Okay, so we're going to focus a little bit more here on friction, and then in this one we'll focus on friction like on an inclined plane. And then maybe we'll get into one where we have like two objects. So anyway, we have this object sitting on an inclined plane, and it's a plane that has there's some friction between the object and the plane, has a coefficient of about 0.1. And so we could solve for the acceleration of the system. And so what we're going to do is we're going to say, okay, well, let's draw a free body diagram. So we have gravity pulling it downward, and then we have the normal force perpendicular to the ramp. Remember that this angle right here is 15 degrees. Okay, now this would be if it was a frictionless ramp, but because there's friction, there's going to be another force pulling back this way, preventing it, kind of like restricting that slide, and so this is the kinetic friction. Okay, so we can write net force equations. Let's start by writing one for x. So remember, we rotate the coordinate plane here. Okay, and so we say, okay, well, the sum of the forces in the x direction, since it's accelerating, are going to be equal to m times a. We'll say that up the ramp is positive, so we'll add these forces together. We have kinetic friction, and we have the component of gravity that's pulling it down the ramp. This component here is mg sine of theta. Okay, so we have here mg sine of theta. We said that up the ramp was positive, so this is positive f, and this is negative because it's going down in that opposite direction. Okay, and then we say, well, I know that friction is just the coefficient of friction times the normal force. Okay, but we can take it another step further here because we can actually solve for the normal force. But in order to do so, we're getting net force equation for y. Okay, so in this y direction, we can say the forces here are balanced because there's no acceleration in that direction. Okay, and then in this case, we have the normal force, and then we have the gravity that's pulling it into the ramp, which would be mg cos theta. Okay, now in this case, we're going to say that up is positive, so this is positive normal force, this is negative right here. So we can solve for normal force to be mg cos theta, and then we'll plug this in for normal force right there. So ma equals mu times mg cos theta minus mg sine theta. And then m will drop out. We can factor out g, and so a is equal to, in this case, g times mu cos theta minus sine theta. And we can punch that in and find that acceleration is going to be 9.8 meters per second squared times something. So here we get acceleration of negative 1.59 meters per second squared. Okay, and there you go. That is friction on an inclined plane. And these, we can make these infinitely complex. We'll do one more of these that will be slightly more complex. And then hopefully that will be enough for you to try some of these out on your own. So here we have an inclined plane. We have a block sitting on it, and then there's a string hooked to it pulling over this pulley to this hanging block of unknown mass. And so for this particular problem, we have a coefficient of maximum static friction of 0.2. So that means that if the force exceeds friction that we calculate using this static friction, then it will cause the block to slide. And so the scenario here is I want to know the max value for m and the minimum value for m that will prevent this block from sliding. Okay, and let's change this from being 0.2 to say 0.3. Okay, and I'm going to let you know right off the bat, I didn't solve this one ahead of time, and so it might turn out that one of these doesn't work out. Okay, so we will go ahead and see. I think it kind of depends on this angle. So the first thing we'll do is we'll say, okay, let's write a net force equation. We know that we're going to need to do one for y for this block right here, but let's draw a free body diagram. So for the 10 kilogram block, we have the weight and the normal force, and then we have tension from this block pulling it right here, so we have T. Now here's where it gets tricky. If this block is heavy enough that it's going to try to cause it to accelerate up the ramp, then what that means is static friction is going to be pulling it down the ramp to prevent it from sliding up. However, if that hanging mass is too light, then static friction will be going the opposite way, because the block will be trying to slide down the ramp and it's keeping it from sliding down the ramp. So depending on how strong this, how heavy this is, or how much mass this has, and how hard we're pulling here, it's going to change static friction depending whether it's going down or pulling up. So like if you pull really hard here, you're going to cause this to start to slide up, and so friction is going to resist that and pull this way. But if you put just a really small amount here, this block still wants to slide down, and so the friction is going to resist that and pull up this way. Okay, and so that's basically what's going on here and what we're figuring out. So to find the maximum M before it starts to slide, we would use this right here, and to find the minimum M, we would use this right here. So we'll set up equations. Let's do net force for y first, so that we can get that taken care of. So y direction, x direction. For this particular block, we still have only those two forces, and so we can say for the block we know, the 10 kilogram block, for y, it's balanced, and it would be equal to mg cos theta minus, so it would be negative mg cos theta plus the normal force. So normal force, again, mg cos theta. Okay. Now, and I guess I should draw a free body diagram for that hanging block. So the hanging block, we just have mg, we'll use big M for this one, and then little m for this one, and then we have tension. Okay, so now I'm going to write an equation for this whole system right here. So the net force for x, we're going to say it's 0 because it's balanced, because we don't want it to slide. So 0 equals, and so we're going to actually ignore tension here because we're doing it for this whole system in this path of travel. Okay, we'll say this way is positive, so we can ignore t here. Okay, so we're going to say, okay, in the positive direction we have the weight of this block, mg. In the negative direction we have the weight of this block pulling it down the plane, mg sine theta. And then we have friction, static friction, that could be going either way depending what we're solving. So plus or minus Fs. So say 0 equals mg minus mg sine theta. Static friction is mu times the normal force. Normal force is mg cos theta. This would be the big M, right? So this would be plus or minus mg, so mu times mg cos theta. Okay, and then from here we can solve. We can try solving when this is positive. We can try solving again when this is negative, see where we get to solve for this m. So you see that we can drop g out of this equation. since it shows up a couple times. And so little m is equal to big M times sine of theta plus or minus mu cos theta. And we can plug that in here. I just did some simplifying, so I moved this and this over to the other side and then factored out the m. And the plus and the minus here, you do this and it will give you the two different values for little m. So when I solve this, I get that m could be equal to, for the maximum value, 8.7 kilograms, and for the minimum value, 4.1 kilograms. So what that means is, again, if this hanging mass is 8.7 kilograms, that's enough to, it would be heavy enough to cause this to accelerate up the ramp. And anything greater than that is going to exceed the amount of strength that the friction can pull back with, so it's going to cause it to slide. On the other hand, if we were to put 4.1 kilograms or less on this side, then what would happen is it's going to start sliding down this way because friction can't pull hard enough this way. Okay? And if there was no friction and you want to know how much strength or how much mass to put here to keep it in place, then you could just eliminate this term that came from the friction, and the amount of mass to keep it in place without friction would be about 6.4 kilograms. Okay, kind of split the difference there. So anyway, I know that that was a lot, and I really hope that this made some sense to you. If you're confused about it, please leave some questions, and I'll try to respond to them. Okay?